Good morning everyone, I am Tony Nakamura. Recent years, calculating uniform heating by induction heating is not easy. Therefore, today I would like to talk about semi-analytical induction heating uniformity. So, now let me begin my presentation. When starting the car with the core, catalyst is not hot. Therefore, toxic gases cannot be purified. Near the future, this is prohibited due to tighter emission regulations. To heat up the catalyst early, we need induction heating with high frequency. Next, I am talking about induction heating system. The catalyst has a large number of micropores. The surface of micropores are coated with catalyst powder. Some of the micropores are filled with heating object. This heating object is loose magnetic material. An eddy current is generated in the heating object by the magnetic field induced from the coil. This eddy current loss heats the catalyst. Next, I am talking about the actual structure model. In order to suppress the proximity effect, flat wire is used for coil. A flat core is placed over the coil to strengthen the magnetic field of inside catalyst. Also, heating objects are uniformly distributed. The next page shows the result of actually heating the catalyst. This is the experimental conditions. Frequency is 100 kHz, and number of coil turns is 3, and the airflow amount is 7.5 10 to the minus third. When the matter was actually heated, temperatures were uneven as shown in this figure. Inside temperature was low, so inside catalyst was inactive and exhaust gas cannot be purified inside. Generally, amount of heating is proportional to square of magnetic field. Actually, I checked the magnetic field by FM analysis. This is the stimulation conditions. RMS current is 229 ampere and frequency is 100 kHz. The result became as shown this figure. So the temperature became non-uniform. How can uniform heating be achieved? As a natural thought, change heating object distribution to address temperature non-uniformly. Specifically, increase the number of heating objects inside than outside. By doing this, I think two effective is obtained. First, flux to the inside increases, therefore increasing inside magnetic field and increasing amount of heat. Second, increasing mass of heating object. In short, simply increasing amount of heating. In this way, uniform heating may be possible by optimizing the distribution of the heating object. Generally, FM analysis is used for optimization of heating object distribution. Eddy current are calculated when considering induction heating in FM analysis. This is simulation conditions. Frequency is 100 kHz. Permeability of heating object is 250. Resistivity of heating object is 2.29 10 to the minus fifth. Using these values resulted in a skin depth of 0.48 mm. This length is fairly small relative to the scale of the catalyst. In other words, the mesh is too small, and the FM analysis takes a long time. Optimizing uniform heating requires changing the heating object distribution in all parts. Searching for each model is excessively time-consuming and impractical. I will talk about my approach to solving this FM analysis problem on the next page. Eddy current loss is proportional to the square of the magnetic field. I thought that it might not be necessary to obtain heating by FM analysis. Also, the total heating amount is proportional to the heating object density. Here, a heating index that can be regarded as a heating amount is set. Heating object density A is volume of heating object divided total volume of catalyst. So, how do you find the magnetic field squared valued? First, we convert to a uniform material with equivalent permeability according to the heating object density. Second, FM analysis to check the magnetic field of the equivalent permeability model. The magnetic circuit is assembled based on the magnetic field distribution. By doing so, the magnetic field can be determined by hand calculation. Also, I divide the volume of the catalyst into two halves, inner and outer. It is difficult to make the heating amount distribution uniform, and I correlate the heating index inside and outside. So this approach takes 3 steps. First, the equivalent permeability must be obtained. Equivalent permeability is obtained using FM analysis, and the relationship between equivalent permeability and heating object density is obtained from a small amount of data. Second, model the magnetic circuit from its equivalent permeability. Considering the magnetic circuit model, the heating index can be expressed as a function of only the heating object density. Finally, we calculate the heating object. Obtain the equivalent permeability from 4 model in this figure. This is simulation conditions. RMS current is 229 ampere and frequency is 100 kHz. Heating object parameters, permeability is 250 and resistibility is 2.29 10 to the minus 5th. Obtain magnetic field and magnetic flux density from FM analysis. So, from this formula, we can calculate equivalent permeability. This figure is relation between heating object density A and equivalent permeability mu. This step builds a magnetic circuit model to represent the magnetic field of the catalyst. First, the topology of the magnetic circuit is determined based on the results in step 1. This figure shows the catalyst with an equivalent permeability of 10. Also, this figure shows the magnetic field distribution of the catalyst cross-section. The catalyst is divided into parts, inside and outside. As can be seen from the figure, the strength of the magnetic field differs in the vertical direction. However, since the gas passes in the vertical direction, the non-uniformity of the amount of heating in the vertical direction is ignored. The magnetic circuit is also composed of 6 segments according to the magnetic field distribution. REO, RCO, REI, and RCI are the magnet resistance corresponding to the vertical magnetic flux flowing through each segment. RAI is the magnetic resistance of the air space corresponding to the inner air area here. In the same way, RAO is the magnetic resistance of the air space corresponding to the outer air area here. In this way, the magnetic circuit was assembled from the FM analysis. Finally, let's talk about step 3. In this step, I talk about how to calculate the heating index. First, I talk about how to calculate the magnetic field. Magnetic field is represented by this formula. Calculated equivalent permeability mu from step 1. And since the area of the catalyst is divided into 2, S is also known. This magnetic flux is expressed by this formula. So, the magnetic field can be calculated. Therefore, heating index can be obtained. Multiple combinations of A in and A out that satisfy this formula were found. So it is possible to calculate the heating object density that can be expected to heat uniformly. First, there are multiple combinations of A in and A out for which uniform heating can be expected from the calculations in step 3. As an example, consider the case where A in is fixed at 0.0348. When A in is 0.0348 and A out equals 0.0101, the heating index is equal inside and outside. In order to clarify the effectiveness of the proposed method, the same heating object density inside and outside were also analyzed as conventional ones. This figure shows the results of total heat generation in the inner and outer regions by FEM analysis. This is simulation conditions. RMS current is 229 ampere and F frequency is 100 kHz. Compared with conventional type, the effectiveness of the proposed calculation method was confirmed by FEM analysis. Finally, I will discuss the results of the experiment. Experiments were conducted to evaluate uniform heating by the proposed method. This figure shows the catalyst with heating objects at A in equals 0.0348 and A out equals 0.0101. These are the experimental conditions. Frequency is 100 kHz and number of coil turns is 3, and the airflow amount is 7.45 10 to the minus third. This is experiment results. From this figure, the inside is sufficiently heated. On the other hand, it is clear that the outside is not sufficiently heated, because heating objects are too far apart. In other words, uniform heating could not be achieved. This is because the simulation does not take heat conduction into account. This is a summary. Next step, since it is known that there are multiple combinations of A in and A out for which the heating rate indexes are equal, a heating test is performed with the combination for a high density on the outside. Thank you for listening.